This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Take a piece of chalk each, and we'll do an experiment with it. But then, sorry? Any colour, just take one piece. Take a piece of chalk each and just pass it back. Okay.
Hi everyone, this is Brian Thompson from, I've just learnt, Worley, no longer Worley Parsons. We've got a computer that's not starting up for us, so Brian's got a lot of objects, he doesn't rely on the overheads, so I'll allow him to just start talking while I get the computer organised. So welcome Brian.
Thank you. So this is just about everybody, is it? Right? Okay, fine. Now look, what I'll do is I'll pass this around. I'll take that out. This is, we're going to be talking about conveyors and bulk materials handling. This is an idler. So on a conveyor, you've got the belt in a trough, and you've got 1, 2, 3 of these, probably a bit longer than this, but it's heavy enough as it is. But you can actually see, quite often these are actually steel, but they're actually going more and more to the plastic or ultra-high molecular polyethylene. But if you might like to have a look. People talk about labyrinth grease seals and things like that. So here's a labyrinth seal there for you to actually have a look at as well. So you get the idea of some of the stuff. Here's a couple of pieces of conveyor belt. You can actually see this is what we call the carcass. So we have a top, the thicker one here is the top cover. This is the inside of the belt. But when it's passed around, you actually just see how stiff this stuff is. And this is a belt. It has to be able to fold up into a trough. It has to flatten to go over a pulley, and then it actually has to be able to get around the pulley. And so you kind of think of how much stress is actually needed to get this to work. So, hey, and I want all these bits back, okay? For the students next year. So have a look at that. This one here, when we actually get the PowerPoint up, the belt actually sits in here like this, and this is an edge. And what we do is we have rubber coming down to seal the edge where we load. We don't, the whole route of the conveyor doesn't have this, but then just to catch the dust. So this is a secondary seal here, and when that actually wears, this is quite a smart piece, you can actually turn it upside down and lock it in and get it to work like that. So you might just be interested to have a look at that. And put on the website, there's 2 handbooks for you. One's called Foundations, and it's got nothing to do with civil foundations. It's all about transfer points. So when we've got a conveyor coming up here and it goes onto this conveyor, it goes there, each of the places where the material transfers from one conveyor to another. This book is about 400 pages long, and it's all about transfer points. But it's good because it's got lots of pictures, and I hate books that have just got text. I like the ones that have got pictures. And so this one actually here says that this, you'll actually see this on page 190 on foundations. But pass that around. So can you get that across here when you're finished? Okay, right. Just about ready to go.
Change the lighting a bit for you, Brian.
Thank you.
Yep. Now, just as per...
Now, so I've got some videos a little bit further in, so you know how to get those.
I'll be able to help you.
Yeah.
I'll just be your assistant.
Right. Okay, so good afternoon. Thanks for coming. I hope this you learn a lot, because this is the kind of stuff that was never taught to me as an undergraduate, and I had to pick it up as I went along, and fortunately I was able to go to some courses, short courses on bulk materials handling, and but then I decided not very many people in the organisation that I was working with knew much about conveyors, and so I started to read, and it's quite interesting what you can get. And a lot of things have actually changed over the years, and maybe we'll come into contact with that. Okay, the picture that's behind me, right, is, yeah, does the pointer work on this? Okay, yeah, okay, you can see the pointer there. Right. Now, this is actually at Iron Duke. This is Whyalla, South Australia. And this is just a picture. I was there some time ago, I think about 2010 or something, because you'll see it. But here you can actually see quite a lot of belt conveyors. Okay, so this is, now this presentation, I'm going to race through some of the bits because this is a presentation I do for engineers in the organisation I work with. Worley has actually just recently bought Jacobs, who's been buying up a lot of companies. Worley have been buying up a lot of companies. We have actually got around about 50,000 employees worldwide. So we're a pretty big consulting organisation. Okay? Right, our objectives. We're going to talk about belt conveyors, where they fit in bulk materials handling, safety issues, design standards. We're going to do a quick preliminary design. That's why you've got the handout. So everybody's got the handout. And some detailed design consideration. And then later on, it'll probably be the following lecture where we get and talk about some alternative types. But here down the bottom, belt feeders are not conveyors, and they're not considered. But first thing I'm going to talk to you about quickly is to show you why. This here is a picture of a, have we got a pointer? I've got a little torch, I think, somewhere that I might be able to use as a pointer. Yeah, this one here. This will do, I think. If I get it down there, okay, that'll do. The batteries weren't working on my laser light at home, and I had to leave it behind. So this will fill in. Okay, look, the green bit across the top, it's a railway train, and this is at Newcastle in New South Wales, okay? This is unloading coal. And so the train actually comes along here, and the coal actually comes down here. So this red stuff here is coal, right? And there's a conveyor here coming along underneath, and it's filling and then goes on to another conveyor. Now, what's happening is material is being piled in here, and it's slowly being withdrawn. So there's a lot of stationary material here. We would like to think that it's all coming down nice and slowly all by itself, but we get a dump, and then so we hold it there. And so that is not like a normal conveyor. This one down here will be a normal conveyor because it's got a continuous feed, and any of the chute work there is not holding up material. So that's the difference. And here, that belt is actually pulling underneath and taking material out, and there's a lot of friction there. And so these things actually work very much more slowly than a normal conveyor belt. Yeah, actually, it's probably 0.5 is probably near the maximum, because sometimes we run a lot of conveyors at 1.6 anyway.
But life easier for all of us. I'll pop back to my office and get you a laser pointer. So you just keep going.
Okay, we're going to be more precise. Right. Okay, so that's why the conveyors are different. Okay, this is just to get it into whereabouts conveyors are. We've got the continuous stuff on the your left-hand side, my left-hand side, and then we've got the discontinuous stuff there. But it actually talks about here the loss factors, and it gives you sort of a bit of a ratio. And look, it's pretty right. Here, I did one of his belt conveyors, and then pneumatic conveyors. In an instant, this is in the Emirates, United Arab Emirates. We put in we could have put in a belt, and it would have. We did a calculation. It was about 32 kilowatts to have a belt conveyor, but somebody decided that they wanted pneumatic, and the horsepower we had to put in was 350. But see, in the United Arab Emirates, they get cheap electricity, cheap gas. They don't care too much about power, but lots of other people do. But so there you've actually got about a 10 to 1 difference in the power. And screw conveyors, because they're actually pushing the material with the screw, there's a lot of wear, and so that's where you'll find that the power on those is a lot more than the belt. Here, obviously everybody knows an aeroplane is going to cost more than a truck. And a train is going to be less than a lot of trucks. And then if you've got to go overseas, well, you can't have a train, you've got to have a ship. Okay, so we'll move on. Okay, I hope everybody, you've got a little bit of familiarity with belt conveyors. Do I need to spend very much time on this? You know that that's the head pulley there, and so that's normally where the drive would be. But then here's the take-up. And it's because we've actually got, you guys have done V-belt drives? Yeah, and you know about the friction around a pulley, and you've got that E to the mu theta situation with the wrap and the, everybody looks blank. So you haven't actually done flat belt or V-belt drives in your transmission course? Oh, well, okay, look. We can't go back and do that. But look, there's enough stuff in the Dunlop book. There's initially when I put it in there for you guys, well, the other students in past years to use, I sort of just quickly dug it out, threw it in, and said, "Hey, that'll do." But in preparation for this, I decided to actually skim read it, and I think it's really a good read. It's got some coloured pictures too, but it's a little bit more technical than the Foundations book. So those two books that you've got that are there now, the Dunlop one is old, but fortunately the way that they've been designing conveyors is, belt conveyors have been around for about 100 years, so it's okay. But look, so there's the take-up. We need a take-up because the belt will stretch depending on, well, even the heat of the day and things like that. So you need this bit here to keep the belt, because you've got to keep the tension here. So yeah, if you haven't done that, are you familiar with a ship windlass on a wharf? You know, those big things that actually go round, and when a ship comes in, they throw a rope and they put a couple of loops around it, and the man actually pulls it, and all of a sudden the ship comes. If you don't pull the rope, now the man's not pulling the whole ship by a long shot, but he actually is supplying sufficient tension to actually get the friction to start to work, and it's the friction on that windlass that actually does all the pulling. But if he lets go the rope, then all of a sudden they lose the friction around the windlass, and so that's why you have to have a weight here to actually keep that. Otherwise, the head pulley will actually just move, and nothing will happen because you haven't got enough contact there to get the stress to work. This bit here, that's just a tripper. And sometimes these are travelling, and so they're on rails, and you can move up and down. And that just means here that you're going to lift it up and then put it on a chute and get it over the sides of the belt and underneath, because you've still got the belt underneath there. And here's the tail pulley, and these other ones here, we call that a bend pulley. This will be up a bend pulley, that's bending around there. That one there, just near the drive, that's a snub pulley, and that just allows us to actually increase the wrap, because if you can increase the wrap, you can actually reduce the tension in the belt, and you'll get the same effect. Okay, and then if you change the material on the pulley, and we'll get to that a little bit further, you can actually, or change the friction, you can actually get different tension. But the thing is, it might sound, stuff's going over your head, but in what I've done here, there's a lot of repetition, and photographs and things like that. So we'll see how we go. Okay, we want to talk about safety issues. Now this bit here, again, okay, just here, that's a take-up. So the belt's actually coming up, going down around the pulley, coming back up. So this is a take-up. But see here, we've actually got what we call a nip point. And if you actually put your hand in there, you won't be able to just pull it out. Unfortunately, at a lot of places in industry, people actually lose their arms, and they're lucky if it actually severs at their shoulder, because if it starts pulling their whole body in, they'd be killed. But I've worked with a lot of people who've actually lost arms in conveyors. So safety issues are very important. This was in Saudi Arabia, and unfortunately safety issues aren't all that important over there. This is underneath where a counterweight weight is, and you'll know more about what I'm talking about. But here, they've taken off the guard. It was guarded, but no, you get some spillage, so you need to get in there and clean it. So let's take off the guard. And unfortunately, I've seen a lot of places around the world where people put holes in guards and all this kind of thing. You guard it so that people don't stick their finger in, okay? Now this is Australian standard. It's listed as a 1755 here. It's been superseded, but all it's done is it's actually been renumbered, and instead of one standard, we've actually got 4 standards now. Now it's important when you have a look at that, all the yellow bits are nip points, and it's because where the belt is held hard against a pulley, then you'll actually get pulled in. But here, where the blue bits is, now that's a horizontal bit, and there's no change in direction of the belt. So there, it doesn't matter so much, because what happens, if you put your hand there, it'll just bump across and it won't get pulled off. I don't think you should try it, but you don't have to guard in those areas. A lot of engineers get pretty lazy, and they just sort of say, oh, just guard the whole lot. Well, if it's short and if there's lots of people, maybe that's okay. But if this is an overland conveyor and going for kilometres, you don't want to have to guard the whole lot if you can help it. And so, and here, there's another straight bit on an incline. And so if you put your hand in, it would just jump across. Here, where we're actually loading, and this is where that piece of rubber that's going around there, that it was a skirt. The skirt is holding the belt down, so so if you put your hand in, it would be a nip point, just because the belt can't lift off. But I think that's enough for that. Here's your counterweight again here, and I've put a note here that you need to keep the mass close to the ground. And you'll think, now why on earth is he saying keep the mass close to the ground? Okay, that's about the nip point. Okay, that'll be the next slide. Okay, we've actually I got this recently and threw this slide in because I thought it was pretty interesting. But there's some shocking things happen here. First off, I don't even know how they loaded it, but you imagine that going for some distance. It's almost like having a big mass, and all these idlers along the side of the belt, they're just going to be belted as this moving along is going to go bang, 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 and poor old bearings are going to get quite a lot of shock. And if this was, thank you very much. Also, if this was actually operating on an incline, that boulder is actually going to start rolling back. And I've seen lots of conveyors on fairly steep angles, but they end up putting big boards up the side, and because they end up getting a lot of rollback. But this one is a horrific kind of thing. And certainly we talk a little bit further, and look, and I'll refer you to the Dunlop manual again. It talks about particle sizes, and normally the rule of thumb would be you have to have the belt about 5 times wider than the maximum size of the material. Well, if you took 5 times that, this conveyor would be about 3 times the width, and then that's very expensive. So it's better to spend a little bit of extra effort on crushing so that you can keep your belt size down. Okay? It's a new slide for you, Colin. Okay, now, Heike, we're going to talk about here, Heike, you might have to help me, I'm glad you've come back, because we're talking about here, so this is a belt at a head pulley, so we're doing a discharge, right? And see, what I want you to do is understand, because a place that I visited Kazakhstan about 12 months ago, and they had heaps of problems with carryback. We call this carryback. Stuff, if it's sticky or it's electrostatic or something like that, stuff actually sticks to the belt and goes back and it gets all over the place. So that's why it's a safety issue. And so we put scrapers there. That's a secondary scraper where we put in, and here's a primary scraper. And now if we can actually get onto those 2 videos, please.
You keep talking, I'll just do that for you.
Yeah, so...
That one?
Yep.
Standard mount?
Yeah, do the standard mount one first. And so if we just do that. Okay, right, now it only lasts for a very short time.
That's right.
Yeah, okay. Now that is that's in the secondary scraper frame, so we just run through it. So the belt, it's actually coming around the head pulley. So what we're looking at is material coming off of the scraper about here. So if you just play that one, yeah. So that's how much, if you didn't have the scraper, that's how much material would go back down to where it came from. But it wouldn't, because it would spill all the way. And you can get a shocking mess. And cleaning up in a lot of plants is a big problem. Okay, now can we show the other one now?
Sure.
And now this one is a primary scraper, and you can actually see the material, see it cascading over the top there. So it's flowing off, but you're still getting quite a lot coming off down here. And so that's a primary scraper, and then we have a secondary scraper here. But so there's the material up there. So
It's essentially flying.
yeah, well,
Or diving.
yeah. So we will talk about the trajectory and things like that a bit further. Okay, so, yeah, done. Thanks. Right. Yep. So now, see, when you get carry back, this is the kind of stuff that happens because, see, all the other rollers on the when you're actually carrying the material, all the idlers or the rollers, and you know that the one has it got to the back yet, or has everybody seen it? How heavy it is and things like that. They're carrying on the clean side, but when you actually come on this is the dirty side, so you've actually got to carry it back, and so that it's the dirty side that comes in contact with the idler roller. And here, and normally on a return, you might just have straights going across instead of troughing. But here, see, you can see the material's built up. And so it's built up here on this side, but it's less on that side. So you've almost got a cone. And so when you've actually got a cone, it means this side here is travelling faster than this. And so normally, like if you put a cone on the floor and gave it a kick, it would go in a circle. Well, here the cone is actually fixed. So what's got to go in a circle? The belt. And so the belt mistracks. And when the belt mistracks, you've got all sorts of problems. So, you know, to try and tolerate something like that without cleaning is not a very good idea, because I'll show you some of the effects. Well, first off, you can get spillage. But look at this. This one here, this is a cover. That's a shaft for a head pulley. So, the head pulley will be in around here, but the belt has actually mistracked to the extent that it's actually cut through the casing. And look, I've been up at places like Mount Isa Mines and all this kind of thing. I've seen where a conveyor belt is here, a fairly wide one, and there's a column here, and an H-shaped cross-section column, and the belt has actually come and just about half cut through the column. And so it's just, the belt is much weaker than the steel, but there's a heck of a lot more belt than there is steel, and so it will eventually get through it. And so that's the kind of thing that can happen. And that's a picture from Kazakhstan, actually. But, right. Okay, now another thing is the belts are rubber, and rubber burns. Now, we can actually spend a fortune on getting self-extinguishing belts, but it's very expensive, and so it's quite often you need to put in a sprinkler system. So this is another safety issue that you have. And my son actually, he works with the same company that I do, and he had a job over in Bulgaria, and they had a belt feeding a furnace. And they said there needs to be some steel plate here so that when there's a power failure and the belts can't continue to operate and get out of the heat, we need to be able to stick in a plate. And they said, oh yeah, we'll do it sometime. Well, during commissioning, there was a power failure and the belt burnt, and it took out that whole piece of conveyor. So, you don't leave some of these things for tomorrow. I'll tell you some other horror stories, and I've been guilty sometimes myself, not doing things quite right. Okay, now, we talked about a belt splice. So this is a belt splice failure. This was a belt, and now what do you think gave all this the energy? So when the belt, so it's a big long one, it's got, well, a big long one's probably got about 5 or 6 joints in it and things like that, but one of them here's failed. What gives the belt the energy to actually stack up like that when the splice fails? Yeah, the tension. Where does the tension come from? The counterweight, right? Okay, good. There. Okay, so this bit here, so where the belt comes over, down like this and up, and then we put a concrete block or something like that to give it the tension. And now these things can be, 5 or 6 tons or something like that. And here, though, what could you do if you want to see the potential energy there is that mass times the height above the ground or where it's going to stop. So what could we do to actually maintain the same tension but take out, reduce the energy? Lower the mass. Good, top of the class. Right, okay. Because one of the other companies that I worked with, this is an international company as well, Fluor, and we used to have a Coke can rule, and sort of say Coke can, about 150 mil. We'd say if you can fit a Coke can underneath the counterweight, well, maybe it's a bit too high in the air. Because so if you've got a big lump and you actually just come down here.
Okay.
Right. Okay. Now, don't put a maintenance platform on the weights, because sometimes here they put the weight so that where the bend pulley is here, then they put the weight right underneath, and so they put a platform so that they can grease the bearings on this drum or bend pulley that it actually moves up and down. But see, if you're actually greasing it and the thing's actually operating and you have a splice fail, you're going to have a quick trip to the ground. And I was inspecting a conveyor over in New Zealand, and it had been like that for 25 years, and it had a platform on it. So, but when I actually highlighted it to them, they could actually see that it was a pretty dumb idea. But in actual fact, it was interesting because I'll quickly show you. A bit of a shock if I introduce this. This was our computer when I went through university. This is a slide rule. Now, a lot of slide rules are straight sticks, But this one here with a straight stick, if you come out too far, you have to go put the stick in the other end and get it right. This one here can actually go round and round. Put it under here. Okay, can you see it? Right. Okay, I'll quickly show you.
You can get a little view there.
Oh,
So you don't keep looking back.
Okay, now I'll show you. See, if I put that one on 2, so I'm going to want to multiply 2 by 2, I get 4. Or if I multiply by 3, I get 6. Or if I come to 4, I get 8, and all this kind of thing. But it could be 20 and get 40, or it could be 200. You've got to actually do a calculation in your head to know where the decimal point goes. And in this one in New Zealand, somebody must have got an answer of 5, and anyway, they put in 5 tonne, and it could have been 500 kilo, half a tonne, and that's what it should have been. When I actually quickly did a check, and you'll be able to do that soon, hopefully, if we get there. Right, okay. Now, there's some other things we need to put in for protection. We have, okay, we've got belt tension detection. Now, look, what we're really worried about is belt slip. And this is where I was guilty one time. A bucket elevator coming up, and there's a pulley up the top, and you normally have to put a detector on the bottom pulley that's not driven to make sure it actually goes. If it's not rotating, you know that you've actually got slippage at the top. And we didn't have an instrument. And I put this bucket elevator in, and it had been operating for about a couple of months, and I hadn't chased up the electrician to put the instrument down the bottom. And actually, the thing stopped moving the belt, and the pulley kept on going at the top, the drive pulley, and it actually just burnt through the belt, and the belt collapsed. So I ended up calling somebody and said, could you come and fix this and do a repair? They did a new splice, and I said to the electrician, look, you've actually got to come and put that detector in, in a couple of days' time, otherwise we're going to have problems again. And I told the people that it was okay for them to actually continue to operate it, and in the meantime, because I'd had 3 months success before, so I thought, it's not going to burn through or wear out straight away. Guess what? Overnight, it wore through the belt again, and it's pretty horrible having to go to your boss saying, I've just had 2 belts burn through because of my stupidity. And so that's one thing there. And now another thing here, this longitudinal slit, particularly where you're actually putting material onto a belt, and particularly on mine sites, because you get all sorts of junk steel coming through. If you actually get a stake, or this here is a big rock, you can actually have a wide belt, and they cost quite a lot of money, but then all of a sudden you get 2 belts, half the width, and that is very serious, and that takes a long time to repair or replace. And yeah, so they try and have detectors for that kind of thing, but yeah, you've got to be careful, and this is why you have magnets over the top to take out steel and all this kind of thing, because you can have real problems with belt. Okay, here's the design standards. Some of the stuff, look, it's amazing that you can't get a design standard. Okay, let me go back. You guys pretty much are taught how to design things from first principles. Well, conveyors, you can't design from first principles. Don't make your own mistakes. Learn from the mistakes of others. And but we haven't in Australia got a design manual for conveyors. We rely on an American design and a British design, and the ISO one is a German, European design. The ISO standard is actually only about 3 or 4 pages, and well, last time I looked at it, there was some mistakes in it. The British one has got some worked examples. It's a really good one if you can get hold of it. But the thing is, the Dunlop one that you've actually got is based on the British and the ISO, and there's a lot of good information in it, okay? So the one that's been superseded we've actually got 4 standards, but they're all about safety. They're safety issues, not design issues, okay? So when you've actually got 4 standards on safety, maybe we're heading towards world's best practice in Australia. And look, I've seen some pretty woeful stuff overseas that's being used. Okay, what we're going to do is we're going to have a quick look. We're going to do a bit of a forensic exercise and just have a look at a conveyor belt. And so we've got some information, and on this one here, so we've got from the load point coming up here, we've got the take-up. Now, I think we might see better. You might be able to see it there. There is the concrete block underneath the bend pulley, but see how far it is there? So if there was a break here, you'd have the thing shooting out this way and flipping over and going everywhere. So there they don't take that rule very seriously, or it's not a rule, it's a recommendation that you should keep your counterweight close to the ground. Okay, so here we've got this is the transfer point. So this is the loading point for this conveyor that we're going to have a look at. And so it's Iron Duke, and we're 2010.
Could you just explicitly point out where the conveyor is and where the material is? I know it's on the right, but just so everyone's...
Yeah, so this is the one that's actually bringing the material in. It is coming in and it's loading. So this is part of the trying to dust suppress at the loading. And then so the conveyor's coming there. Here's some idlers, but we've got the next picture, and there. So there's the material on the belt. Okay, now we're going to start talking about some things like surcharge, sag, maximum lump size, and edge distance. Okay, so edge distance here, because if you don't want stuff going over the edge, so most conveyors, and we'll start talking a bit about this thing here, because, or maybe we're just a little bit premature to get in here, but it actually is all about across, in the middle here, about cross-section, or back to here.
Right, that's okay, I can do that part of it. Just keep talking.
Okay. Now we're talking about here. Now you can actually see that it's very, very straight. There's not much fluctuation along here, so that's fairly straight. The edge distance is fairly good. But now when we talk about surcharge, and I'm going to show you a slide soon, that's talking about humping up the material here to get more carrying capacity. Here you can actually see that this is pretty flat across here, so there's minimal surcharge, right? But the maximum lump size, we've not got these big boulders that are going to roll back, and certainly, say if that's the largest size, the belt is lots wider than 5 times the maximum lump size. Okay, here, this is a slide. So now we've actually got that's an idler roll, Now, so see what we was, so you've got the edge distance here, and so what we were doing here in that picture, the previous one, it was pretty flat along here, so we were missing out on what we call surcharge. And this is actually out of the Dunlop manual, and there's lots of different shapes and things like that. Sometimes they have a longer one here and shorter ones here and that kind of stuff. So they'll actually give you the formula to do the calculation. The sheet that you've got says here, cross-sectional area of burden is for 30-degree trough and 20-degree surcharge. So that's your troughing angle there, and the surcharge there. So that's 30 degrees and 20 degrees. So that's what this table is set up for, right? Okay? Because that's going to be critical. And so, now, the table also allows for continuous flow. But see what's happening here on this conveyor? We've got intermittent flow here where there's no material here at all. And that's because the material here is being raked off a stockpile with a reclaimer. You can actually see those little bits there. They're the sort of the rakes, and they're on a boom here that actually comes down and pulls the material. So you're actually getting it coming whoosh, 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 and even like coming out of a bucket elevator. Each bucket, as it discharges on the conveyor, you'll see the pile going out and in and out. And so what you've got to do is when you select a belt, you've got to make sure that you allow for this, because this is changing. Here, you need a wider belt. Oh, no, we could get away with a smaller belt, a wider belt, a smaller belt. So you can't, and particularly when it gets confusing when people say that we're going to do 1,500 tonne an hour, but you don't know whether that 1,500 tonne an hour is continuous for the whole hour or is it intermittent. And they have a stop every 5 minutes or something like that for 5 minutes. Those kind of things are really important and shouldn't be overlooked, because here this conveyor takes multiple product. And so if you've got Coke, for instance, it's a sort of a fine scoria type material. It's got a density of about 0.8. So then if you've got 500 tonne of that, it's going to have much more bulk than if you've got 500 a tonne of something that's actually got a bulk density of 3 tonne a cubic metre. And so and this is where, this one here was in Kazakhstan, and they actually had to speed up the conveyor because they were getting problems because it hadn't been properly sized. But it's not only Kazakhstan. I was down in Tasmania at Temco, and they had material going up a conveyor belt there of all different densities, and so you need a wider or a narrower belt depending, and you're not going to change the belt. You've got to get the belt that's going to suit all the product. Okay, now this is just to show you that, so the belt we're going to look at is this one here. So there again, that's the take-up, but it's got people in here so that you can actually see that what we're doing is a fairly sensible kind of size belt. Here's the drawing for it, and again you can, so you've got the feed, we've got the inclination, we've got the take-up. So what we're going to do is we're going to do a quick check of the calculation with our pieces of paper here. Now, this one here is a data sheet for the conveyor, and so it tells you all about all the idlers, all the bed pulleys, and that kind of stuff. Here we've got a tension diagram. We'll have a look at that a little bit later. That's the one there we want to have a look at the moment. Okay. So that's the bit up there that we're looking at. So here now, if you have a look on this page, that's okay. I'll do it on here. Right. Okay. Yep. Right. Now, we've still got that one there. Right. Okay. Now, what I'm trying to show people here, so this is a general one. On the back, you've got a clean one that you can use. So if you scan that, but this one will tell you quickly how to use. So you come in on the red ones and you come out on the blue ones with your information. Now, what we're doing here is we're changing from a gravimetric, so that's tons, into a volumetric, because belts are volumetric things. And this is where people get so confused, particularly when you change from one material to another. Whatever you say in tons, it all depends on what the density of the material is. So, if we go into a volumetric system, so this bit here, this bit here is actually changing it from, this is gravimetric, we're coming over to volumetric. And so now if we come in here at these about 1725, so look, make it easy, we'll come in at 2000 here, right? Okay, now on there, we need that extra bit. Okay, the density there is 2 to 3 tons. Now, if we're actually going to work on volume, which is the best one for us to use, the smaller density or the greater density? What's going to give us the biggest belt? Somebody, heck, I haven't lost all of you, have I? because look, if we pick, okay, let's have a quick look. Okay, we're coming at 2,000. Now, say if we say it's 1 tonne per cubic metre, we come down here, then we come down this line here, and then along here, and so it says that at 1 tonne, 2,000 is 2,000, and that's what we would expect because we've just multiplied or divided by 1. Right, okay, but now if we come under 2 and come down, we come along to here, and then we come down 2, we come down to here and come across, we come out at 1,000. Okay, so that's the volumetric capacity. Now if we come down at 3, come down here, we come straight across at 3 because we don't actually come across, and we come over here at 630 volumetric capacity. So to be safe, it's best to take the worst case. So the worst case for us here is to take the 2, right? Okay, so now we come down here, we come 2, we come across here, we come down, and we come out at 1,000, right? Okay, everybody with me? Yeah. So we come to here, then we come down here, and then across here, we've got 1,000. Okay, now, see, this is really good. You can get computer programs that will do all this kind of stuff in the background for you, but you haven't a clue what's going on. You shove the information in, you get an answer, but you've got no idea about the sensitivity. When I show other engineers who've been using computers and things like that, and they see this old chart, they think, hey, wow, this is good. Because now what we've got here, we can actually see along here, these are standard belt widths, okay? You don't dream up belt widths for yourself. And so now we're not quite sure, but they've actually selected here, the belt width was 1050. Now you kind of think, well, for crying out loud, why did they pick that? But I think it's actually 3'6" in the old Imperial. I didn't actually check that out, but it sounds about right. Okay, so that's why we've got a funny odd number in there. But the thing is that if they've got a whole heap of other belts that are about this size, they don't want to introduce another belt. They want to just standardise on the belts that they already have. So there's a whole heap of reasons why they might have picked that. But now that they've actually picked that, we've got 1050. If we come down here and we come into our line, we actually see that the speed then is 2.3. And they've actually got a speed here of 3.1. And we say, hey, now why would they possibly be going a bit faster? And we've already talked about it, and I'm wondering if you can remember, what did we say about something here? Because remember here, the cross-sectional area is based on that. What did we actually find when we had a look at the photograph? The burden, remember? The surcharge. The surcharge was flat. And so then you have to reduce, because this is allowing for a 20% surcharge. So if you actually, because we're losing on that volume, then we have to go a little bit faster. Okay, can you understand what's going on there? And so we're happy at the moment anyway that 3.1 will be probably about okay. We'd have to go in and do a more thorough calculation. But this is a really good thing to get you close, and quite often this will actually get you on the high side of where you want to be. But okay, so we're saying 1050 belt, that's probably about right. 3.1 seems a bit fast, but because they haven't got the surcharge and it's flat, and we've got, well, we put in 20,000 tonne per hour, it's close enough to 70. When you actually do bulk materials calculation, you don't need to worry about too much of the finesse, because the stuff changes all the time. The densities change all the time, but mind you, when you pick your power and stuff like that. Okay, let's have a look. So, we've done that. Right, so it's dependent on the maximum lump size. Here, we've done that. Okay, we're moving on.
Is that time tether?
Sorry?
It's about time to stop, right? We've got 1 minute to go.
Oh,
Go on.
okay, well, now, because you've got some chalk, we're actually going to talk about a failure. I'll just get a piece of, where's some chalk? Because this will be for the next time, because we're going to talk about a shaft failure. And I just want you to, I don't know whether you've done it, but when you did Moore's circle and that kind of stuff, this is where you actually get your angles from Moore's circle and stuff like that. I want you to get your piece of chalk, and so when we're going to do it in pure bending, we're just going to go like that and bend it. Okay, break it. Have you broken it? Now, when you have a look at it, this is forensic engineering, right? So when we break it, it's fairly straight, right? Straight surface. Now, get a piece, the other bit now, and now this time we're going to break it in torsion. I want you to twist it so it breaks in torsion. And then you got Okay, I got it. Now when you actually break it in torsion, you get it. What's the angle approximately? 45 degrees. Hey, you got that blue one is pretty beautiful. Okay. That one there, see, that's on Moore's circle. That's where you expect the shear stress to be at 45 degrees. And so when we have a look at next on Thursday, when we had this 10-inch shaft that fractured, and we'll have a look at it forensically, why the shaft actually broke. Okay, now could you please dispose of the chalk carefully, responsibly, environmentally friendly into the landfill bin. And yeah. Well, have I got? Are we going to have other people moving in?
I'll be coming in about a minute. So, and the class has probably got the next lecture to go to. So.
Yeah. Okay, because what I want to do next time, we've finished, just about finished the example, we'll work out the tensions in the belt, but then we'll have a look at some other bits. But I want to talk to you about materials too, because there's a lot of strange things, and I've got a whole heap of other things that I can show you about materials.
So Brian, thank you very much.
Okay, so if I see you on Thursday, I'll know that you've been a bit interested. If I don't, well, sorry about that, and all the best for your exams at the end of the year. Right on. Okay, hope to see you on Thursday.
Just turn that off.